Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation and another interesting topic that is understanding magnetization inrush during energization of a power transformer and how to implement the required protective relay settings to ride through the magnetization inrush condition during energization of the power transformer. My good name is John Kweku Amuotu, and I'm a professional electrical engineer for 30 years, and I'm based in the United States of America. Now let's right on to the next slide, and that is absolutely the outline for my presentation. The first thing I want to talk about is what is the phenomenon of magnetic inrush. And next, we'll move on to the conditions that can cause magnetic inrush currents to flow during energization of a power transformer. Next, we'll take a deep dive into the equivalent circuit of a power transformer. Then the phenomenon of a magnetic inrush condition. Then we move on to talk about the factors that can determine the magnitude of the magnetic inrush. Then the effects of magnetic inrush when you have a very high peak current of magnetic inrush current and its effects on the power transformer. Typical effects are basically high saturation, which can cause a lot of heating inside the transformer. Next is the required protective relay settings to ride through the magnetic inrush condition during energization of the transformer. And typically, as part of the differential protection relays, we basically set the second harmonic, the fourth harmonic, as a function of the fundamental frequency. Then to override overexcitation condition during energization, we utilize the third and the fifth harmonic as a function of the fundamental frequency to set the relay to inhibit the relay from basically sensing the inrush condition as a fault condition. Okay, so now let's move on to the next slide and we'll talk about what magnetic inrush is and the definition of magnetic inrush during energization of a power transformer. As you know, if you energize a power transformer, right, the high voltage side is connected to the source. So once you apply that voltage to the high voltage side, the low voltage side is open circuited. It's not connected to any load. As soon as you energize the transformer, you will see a very high peak current, which is transient in nature, right? Has a higher order of frequencies in a magnitude of about 10 to 12 times the full load amperage. That will flow through the transformer at the instant of switching with the secondary side open circuited and not connected to any load. And for that matter, for larger power transformers, right, you can see peak current to the tune of about up to 30 times the full load amperes, depending if by the time that you energize the transformer, there was a residual flux that was embedded in the core of the power transformer. And also depending on the instant of energization on the sinusoidal wave. As such, because of this high peak current, you're talking about between 10 to 12 times the full load amperes or up to 30 times of the full load amperes, the protected relay, the differential protected relays will misinterpret or mischarge it as a fault current. Now let's look at the difference between an inrush current and an actual fault current. An actual fault current has a lower magnitude of second harmonics and fourth harmonics and third harmonics and fifth harmonics, whilst an inrush current has a higher order or magnitude of second and fourth and third and fifth harmonics. So that is the difference between a magnetic inrush current and an actual fault current. So that is basically what we use to distinguish between a magnetic inrush condition during energization of the transformer and an actual fault condition that basically goes through the transformer. Now let's move on to the conditions that can cause magnetic inrush currents to flow through a power transformer. The first one we want to talk about is the energization of a power transformer. That is, if you have disenergized a power transformer, right, taking it out of service, then you are bringing the power transformer back to service. So you energize it with the low voltage side open circuit. Next one is energization of the power transformer if the power transformer is connected in parallel, right? That is, if you have two transformers that are connected in parallel, right? And one is already energized and operating. Then you apply energization to the second transformer, right? So when you do that, the transformer that is already in service will experience a phenomenon called sympathetic inrush condition. And that itself can cause the power transformer to trip if you don't have the right settings in place. Next is voltage recovery right after a fault clearing. That is an external fault. If you have an external fault and the protected relays basically clear the fault, then after the voltage recovery, the power transformer might experience a magnetic inrush in the process of being energized. Now let's move on and talk about the equivalent circuit of a power transformer. Very, very important. As you know, that the equivalent circuit of a power transformer is generated or created after performing the temperature rise test. So that is when the open circuit test results and the short circuit test results are added as part of the testing for the temperature rise to achieve the required temperature rise above ambient for the oil and for the winding temperature. So after that, the equivalent circuit of the power transformer is derived. So now let's go through the equivalent circuit, and we'll see all the parameters that basically comprises of the equivalent circuit of a power transformer, right? So the first one is the resistance, okay? So as you can see over here, R1 is the resistance of the primary, right? So the measured resistance or the calculated resistance is what is utilized to calculate the copper losses. Next is X1. X1 is the leakage reactance of the primary winding. In this case, the high voltage winding. Next, this branch is the magnetization branch. And what does the magnetization branch mean? The magnetization branch is basically the core material of the power transformer, right? So, as you know, magnetization branch has basically the flow of eddy currents and hysteresis laws, right? So that itself forms the resistive branch and the reactive branch, as you can see over here. This is the resistive branch, and this one is the reactive branch. So we have a resistive current flowing through here, and the magnetization current flowing here. So the total combination of the resistive current and the reactance current basically comprises of the no-load current that is flowing through the core of the power transformer, also known as the magnetization branch. Okay, so this branch is basically the high voltage winding that is wound on the length of the core, right, in three phases for a three-phase transformer, right? Okay, then this part is the low voltage side. Okay, in this case we are considering a step down transformer. That is, we are stepping the voltage from a higher voltage to a lower voltage, right? So the test ratio or the voltage ratio is N2 over N1, right? Okay. So now this part is the secondary side, right? So the secondary side also has the winding resistance, right? So this winding resistance, and that is what is utilized to calculate the copper losses to perform the temperature rise test to derive this equivalent circuit for the power transformer. Next is the leakage reactance on the secondary side, right? And this one is the connected load, right? Okay, but we're talking about magnetization inrush, the load is not connected. This one is basically an open circuited condition. Okay, so we have a circuit for the open circuited condition. So now let's talk about the phenomenon of magnetic inrush, right? Okay, so this switch basically mimics a circuit breaker, right? Okay, so we have a circuit breaker that is going to be energized, that is going to be closed to energize this transformer. So once we close this circuit breaker, right, we have applied voltage that is impressed on the high voltage side, right? So once this voltage is applied to the high voltage winding, this is the high voltage winding over here, right? Then we have a current that is going to flow, and that flow of current that flows through the core basically creates an EMF, electromagnetic field, right? And that electromagnetic field is going to go through the conductors of the low voltage winding and induce a voltage here. But in this case, our secondary is open circuited, right? So no current is going to flow. We don't have a load connected, right? So we will have an induced voltage, a voltage in the high voltage winding, and another induced voltage in the low voltage winding, but current is not going to flow. So the differential relay, what is it going to see, right? The differential relay is going to see a current flowing on the high voltage side, but no current is going to flow on the low voltage side. So the differential relay is going to see it as a differential current, right? And will provide a trip signal based on that if you don't have the right relay settings in place to inhibit the components of this inrush current that is flowing. As you can see over here, this is my sinusoidal voltage that I'm applying to the high voltage side, right? With a magnitude of maximum magnitude of Vm, and basically your sinusoidal wave signal is changing, is alternating, right? Okay, so from the negative to the positive, right? Okay, so as we applied the sinusoidal voltage to the high voltage side, right? You have a flux that is going to flow, right? Okay, so that flux will be your transient flux that is going to flow, right? Okay, then we also have a flux that is going to flow during steady state condition after the inrush condition has subsided. So a total amount of flux or magnitude of flux is going to comprise of the inrush flux plus the steady state flux. As you can see over here, the flux is lagging the sinusoidal voltage that we have impressed on the high voltage side by 90 degrees. Okay, so now let's talk about where we're going to have the highest peak of flux and where we're going to have the lower peak of flux, right? Okay, so for instance, if we energize the transformer at this zero crossing of the sinusoidal wave, what is going to happen? We're going to have a very high inrush current. Very high inrush current. If we energize the transformer at the maximum of the sinusoidal wave at this instant of the sinusoidal wave, we're going to have a lower amount of inrush current flowing. And if we energize the transformer in between the zero crossing of the sinusoidal wave and the peak of the sinusoidal wave, let's say across here, then we'll have an inrush current that is going to hover between the minimum and the maximum, right? If this is the maximum and this is the minimum, and if we energize the transformer in between this instance, then we'll have an inrush current that is going to be in between the minimum and the maximum. So that itself tells you the magnitude, or plays into the fact of the magnitude of the sinusoidal current. Okay, so right here at omega t is equal to pi, right? That is when we will have the maximum flux, the peak flux, right? And we'll have 2 times the peak flux, right? Okay, so if we have 2 times the peak flux, right, at the instant of energization plus the steady state flux, so this will comprise the total quantity of magnetic inrush current. On the other hand, there are times that when you disconnect a transformer or de-energize a transformer by tripping the circuit breaker, right, there is something they call residual flux, right? And the residual flux, there are strategies or other techniques that are used to remove that residual flux. On the other hand, if you don't remove that residual flux from the core, then you apply an energization to the transformer, then you get a total of phi r. So a total flux of phi r plus the maximum, the peak flux, that is twice the peak flux, plus the steady state flux. So this is what you get when you have a residual flux embedded in the transformer core before you energize. So that itself tells us that, you know, like I indicated, that it is the magnetic inrush current is much dependent on the amount of residual flux that is in the core before you energize the transformer. Okay, so now let's talk about the factors that determine the magnitude of the magnetic inrush current. Right. Okay. So the first one is X over R ratio from the source, the utility source, up to the location of the power transformer. So now let's draw a circuit for the utility. It is represented by this symbol in most modeling softwares. That is eta, P star, SKM, etc. Right? Okay. So the utility has a short circuit capability, right? And that short circuit capability can be represented by MVA, short circuit, or I short circuit, right? Okay. So the MVA short circuit, you can have a maximum or minimum, right? And for the short circuit current, you can have a maximum or minimum. Then, as part of the short circuit component, you can have a single line to ground short circuit or three-phase bolted three-phase fault short circuit contribution. Then you can have an X over R ratio of the utility source. And what does the X over R ratio means, right? Okay, so see it this way. This utility source that is feeding this transformer, right, has a lot of generators, right, from all networks that are basically forming a power system network, right? So a generator is here, a generator is here, generator is here, transmission network is here, and within the transmission network there are a lot of power transformers, right? So all these form an X over R ratio, right? You can determine the X and the R of all this power system network, which basically comprises of generators, motors, transmission lines, cabling, right? So that itself determines the short circuit, the X over R ratio up to this point, okay? From the utility, right, up to the high voltage side. If this is the high voltage side of the transformer, right, and this is the low voltage side of the transformer. Let's say if we have a transmission line, right, that basically, right from the point of common coupling of the utility up to the high voltage circuit breaker, and from the high voltage circuit breaker to the high voltage side, right? That itself, the transmission line or the feeder cable also has a reactance and resistive element. So they also form an X over R. Okay. Then within the transformer itself, right, the transformer has windings, right, has a high voltage winding and also has a low voltage winding. This winding also have a resistive element, that's the winding resistance, and reactance elements from the leakage current, and also has an impedance, which is the square root of X squared plus R squared, right? That forms the impedance. So from there, we can find the X over R ratio of the transformer. So the total X over R ratio is all that up to the transformer. So what does the X and the R do, right? Basically, it's more like a time constant. They impede the amount of short circuit current that flows from the utility that is going to go through the transformer during energization, right? So that's how the X over R ratio play a factor. So the higher your X over R ratio, the lower your magnetic inrush current, right? The lower your X over R ratio, the higher your magnetic inrush current. Okay, so that itself explains how X over R ratio plays as a factor in determining the magnitude of the magnetic inrush current. Next is residual magnetism. Remember, I made mention that residual magnetism plays a great factor in determining the peak magnitude, how much magnetic inrush current that you will experience or the transformer will see during energization. Okay, so let's say we have a breaker, right? Okay. Okay, so we have applied voltage, right? And we energize the high voltage side of the transformer, right? With the low voltage side or open circuit, right? Okay. If we de-energize this transformer, right, that is open the breaker, and based on the instance, the switching off of the sinusoidal wave, right? If we have a sinusoidal wave, right? Remember I made mention about the instant of switching off, right? We can have something they call residual magnetism. That is going to be embedded in the core of the power transformer. Right at the time that we are taking the transformer offline, we have de-energized the transformer, right? Okay, so you have a transformer, you have de-energized it, right? You have taken it offline, right? But you did not basically pay attention to the point of instant of switching, right? There are other schemes that there's something they call controlled switching, and this is a scheme that some of the utilities or the industries utilize to mitigate residual magnetism from being embedded in the core by basically switching off at the peak of the sinusoidal wave so that you can have a zero residual magnetism, right? Okay, so for instance, if you don't have that scheme or that device in place, right? And you switch off or de-energize the transformer at the zero crossing, what is going to happen? You will have a very high residual magnetism, because this is the maximum. Zero crossing, that is where the peak flux is basically located. So that is when you have that embedded residual magnetism inside the transformer. Then, when you're ready to energize the transformer, right, you close the circuit breaker. What is going to happen, right? Let's say at this time you are energizing the transformer at this instant, right, a little bit above the zero crossing. Already you have this amount of a residual magnetism embedded in the core, and this time you're going to energize here. What happened? Your peak magnetic inrush current is going to be very, very high. So that itself basically tells us how we are able to achieve 10 to 30 times the full load current as the magnetic inrush current. Okay. Next factor is the instant of switching, and I made mention over here, right? And I think I've explained a little bit about it, but let me go ahead and explain a little bit more, right? Okay, so we have a sinusoidal wave, right? That goes through the zero crossing, right? Okay, so let's say if you are energizing this transformer at this location, right, of the sinusoidal wave, right? Okay, so at this instant, that is where we will have the peak magnetic inrush current flowing. On the other hand, if you energize the transformer at this location of the sinusoidal wave, right, this is where you will have the lower magnetic inrush current flowing. Okay, in between is where you will have in between the maximum and the minimum, right? Okay, so that itself explains the reason why the magnitude of our magnetic inrush current is much dependent on the instant of switching of the sinusoidal waveform. The instant that we switch the circuit breaker, we turn the circuit breaker on. Okay. Then our next factor is the size of the power transformer. Yes, that comes into play, right? Okay, so as you know, we have a different MVA output and sizes of transformer, right? Ranging from, let's, for instance, 50 MVA, right? 100 MVA, 200, all the way, let's say, up to about 1,000 MVA, right? Okay, so a transformer of that size, 1,000 MVA, that's a huge one. Compared to a transformer of, let's say, 100 MVA, the 1,000 MVA will have a very high magnetic inrush current during energization. Matter of fact, let's say close to about 10 times the full load amps of the transformer. Whilst a transformer rated at 100 MVA will basically see inrush current, let's say about 10 times the full load amps. So that itself explains how the size of the power transformer plays a factor, right? It plays a factor in the size of the core material, in the area of the core material, right? Okay. Now let's talk about the area of the core and the design flux density, right? Okay, so for a larger transformer, and basically it comes to the same explanation, right? If we have a 1,000 MVA transformer, basically the core size is going to be very big, very huge, right? Compared to a 100 MVA transformer. So a core like that, basically the size of the core will basically require more inrush current to be able to magnetize the core compared to 100 MVA, right? We are comparing a 1,000 MVA transformer to a 100 MVA transformer, right? Okay, so the size of the core of a 1,000 MVA transformer is far larger than that of a 100 MVA. that of a 200 MVA, that of a 300 MVA, all the way up to, let's say, about 900 MVA. Right? Okay. So because of this larger size of core, it's going to require a larger magnetic inrush to be able to magnetize the core to achieve the required voltages on the primary side and the low voltage side, which is the secondary side. Also, the design flux density plays the factor, right? As you know, the larger the size of the core, the higher the flux density, right? The flux density, which is given in Tesla, is given by a flux over A. Next is the core material, right? Okay. So for the transformer, we have different core materials, and these days, to make the transformer more efficient, there are so many core materials that have come into place. And also the core buildup. One of the typical examples that I can give is basically the step ladder core buildup, right? Okay, so that itself makes it easier for the traversing of the flux through the core, right? Yeah. So as you make it easier for the core to flow easily through the core material, that itself will impact the amount of magnetic inrush current that you are having. Next is the utility source, short circuit current, right? And I think I explained it over here. The higher your utility short circuit current, which can be given in MVA short circuit or current short circuit, the higher will be your magnetic inrush current that is going to flow through the transformer during energization. Now let's talk about the effect of high magnetic inrush current, right? Okay, so you have a transformer, right? And you have a circuit breaker right here. And you have a winding right here. You have another winding that is here, right? Okay, and this is the core, right? Okay, so we have the high voltage winding here, the low voltage winding, right? Okay, with the low voltage side open circuited, right? And this is your circuit breaker, right? The circuit breaker is represented as a switch. Okay, so we apply a voltage to the high voltage side, right? Okay, by energizing this circuit breaker. So as we energize this transformer, right, current is going to flow, right? And that current is going to flow through the core, and it's going to create an electromagnetic field that is basically going to link the windings of the low voltage side and create another voltage here. But because there's no load connected to A, no current is going to flow on the secondary side. There's going to be current flowing on the high voltage side, and I indicated that this makes it vulnerable for differential protective relays to trip because of that. And that is why we put in all the required settings to prevent such relay from tripping on high magnetic inrush current. Okay, so if the inrush current, remember I made mention that sometimes if you de-energize a transformer, right, and let's say a transformer trips online, right, and you decide, depending on the instant of the sinusoidal wave where the trip occurred, right, there might be some residual flux that can be embedded in the core, right? Let's say if the transformer tripped on this area of the sinusoidal wave, so definitely there's going to be some residual flux, right? Okay, so after that, let's say you do all your checking and do all your testing, then you decide that okay, the transformer it's okay to be energized. There's nothing to worry about. There's no fault inside the transformer, but it was just a protective relay that basically spuriously tripped. So if you decide to energize this transformer, already there is residual flux that is in there, right? That is in the core. So once you energize this transformer, there's going to be very high peak magnetic inrush current. Let's say you're talking about, let's say 20 to 30 times the full load current of the high voltage side. Why? So what will happen? Right? You have the magnetic magnetization core right here, right? This is the resistive part. This is the reactance part, right? Okay, so we have the magnetization current, I0, that is going to flow, right? Okay, so that high inrush current basically can saturate the core, right? Can saturate the core. And when it saturates the core at that instant, the inductance of the magnetization branch, which is the core material of the transformer, will decrease. As such, it can cause a lot of heating inside the transformer and can result in your core basically getting shorted and failing whilst the transformer is in service. Okay, so that is very important. So that is why we don't want the core to be saturated, and there are measuring schemes out there that basically is able to identify a saturated core. On the other hand, it can also have measuring instruments detect erroneous measurements and cause protective relays also to trip based on that. Next, it's what are the required relay settings that we need to implement to ride through this magnetic inrush condition that we experience. Every transformer experiences during energization. First of all, let's talk about the components of a magnetic inrush, right? Okay, so magnetic inrush, as you energize this transformer, right? Got my circuit breaker here, my transformer. Okay, this is my high voltage side, this is my low voltage side, right? Okay, and this is my circuit breaker on the high voltage side. Okay, I impress a good old voltage on the high voltage winding as I close this switch, which is the circuit breaker, right? Okay, with my low voltage open circuited, right? Immediately I apply that, I'll see inrush current flowing, right? That inrush current has the following components. It has the fundamental frequency current, it has the DC component, it has the second harmonic, it has the third harmonic, it has the fourth harmonic, it has the fifth harmonic, it has the sixth harmonic, and it has the seventh harmonic, right? Okay, so the magnitude of this harmonic currents basically decreases as you go to the higher order harmonics, right? Okay, so as the magnitude of a second harmonic content is very high compared to, let's say, the sixth harmonic. Okay, so this is basically for magnetic inrush, right? Okay, for instance, the second harmonic content can be about 20 to 30% of the inrush current, right? The fourth harmonic current can be, let's say, about 10 to 15%, right? Okay, then your third harmonic current, let's say about 10%. Then your fifth harmonic, let's say about 8%. Okay, so let's consider a fault condition, a fault current, right? A fault current also has all these components, but the second harmonic content is lower. Let's say a fault will have a second harmonic content, let's say 5% to, let's say, 6%. Fourth harmonic content, let's say about 3% to about 4%. So that is the key, right? So it means that I can utilize the percentage content of the second harmonic and the fourth harmonic to distinguish between an inrush condition and a fault condition, right? Okay. For a magnetic inrush current, right, I have a second harmonic content, let's say about 20 to 50%. I have a fourth harmonic content about 10 to 15%, right? Whilst for an actual fault condition, I have a second harmonic content of about 5% and a fourth harmonic content of about 3 to 4%. So I can utilize a setting of about 20% in the differential relay and 10% for the fourth harmonic to inhibit, basically prevent tripping of the differential relay, so that I can ride through my transformer during energization. So that is how the protected relay is able to distinguish between a magnetic inrush condition and an actual fault condition. On the other hand, let's say during energization, right? And let's say you have this magnetic inrush current flowing, and at the same time you have a fault condition occurring, and that can happen, right? Same thing. That is how the differential relay will distinguish between that and be able to identify and see that, yes, based on the measured harmonic content of the amount of current that is flowing, this is a fault condition. Though I have an inrush condition, I still have a fault condition, but this time I need to trip the transformer because of the measured percentage content of the second and the fourth harmonic. On the other hand, if I don't have any fault current flowing and I have that amount of inrush current of the second and the fourth harmonic as a ratio of the fundamental current, then I have an inrush condition. So I'm not going to trip the transformer. Yes, I'll ride through it and energize the transformer. That is what the relay is going to do. And that is what the relay has been programmed. So that is what they call second harmonic inhibit or blocking, or fifth harmonic inhibit or blocking. So that is a ride-through phenomenon to allow you to energize the transformer. First, yeah, energizing. Another condition that can occur during energization is overexcitation. Overexcitation. Right? Okay. During energization, yes, because we have a no load, right, condition. No load is connected over here, right? Okay, and your low voltage side basically is energized and has some voltage in it, right? And no connected load, right? So you can experience an overvoltage condition, which can basically result in overexcitation. So I'm energizing this transformer, right? And I have a third harmonic and the fifth harmonic, the odd harmonics, right? The third, the fifth, and the seventh, right? How do I distinguish between an inrush condition that has such components and an actual overexcitation condition that can saturate my core and basically create heating? I have to determine the allowable amount of overexcitation current due to odd harmonics that flows through the transformer during energization, and use it to distinguish between that and an actual overexcitation condition. Let's say if you have a connected load, and let's say you have a load rejection condition that can result in an overexcitation, or voltage recovery after a fault that can result in an overexcitation condition. So to distinguish between an inrush condition that has a higher order of a third, fifth and seventh harmonic, we utilize the settings to distinguish between that and an actual faulted condition, which is an overexcitation condition, to distinguish and prevent the protective relay, the differential protective relay, from tripping on inrush conditions. Another settings that you can utilize to ride through the inrush is adding a little bit of delay to the differential settings, right? As you know that differential protection is the primary protection for the protective relay, right? And most often than not, the differential settings is an instantaneous settings, right? No time delay, right? But what you can do is basically adding a little bit, let's say 0.01 seconds to the differential settings to allow the inrush current to subside, right? Because it's a transient current, and it subsides at a very shorter time. With that, that comes to the end of my presentation, and thank you so much for your great listening years, and look forward to the next presentation topic. And if you like this topic and the presentation that I made, select the like button in the YouTube and subscribe to my channel. Thank you so much.